code addresses the application of series ratings for overcurrent devices, such as circuit breakers or fuses, specifically in relation to motor protection. Series ratings involve determining the overall interrupting rating when multiple overcurrent devices are connected in series. The code explicitly states that series ratings are not permitted when motors are connected on the load side, meaning the downstream side, of a high-rated overcurrent device, and simultaneously on the line side, the upstream side, of a low-rated overcurrent device. This prohibition stems from the potential inadequacy of the low-rated overcurrent device in providing sufficient protection for the motors in this specific configuration. To illustrate this, consider a motor with a full load current rating of 10 amps. Imagine a scenario where a 20-amp circuit breaker is installed on the line side of the motor, while a 10-amp fuse is placed on the load side of the motor. If the motor were to draw 12 amps, exceeding its rated current but below the circuit breaker's tripping threshold, the 10-amp fuse would blow, as it is designed to interrupt the circuit at that level. However, the 20-amp circuit breaker would not trip because the current draw is below its activation point. This situation presents a significant risk, as the motor could sustain damage due to the prolonged overcurrent condition before the upstream circuit breaker eventually tripped, if at all. The appropriate method for protecting motors in such instances involves utilizing a single overcurrent device with a rating that matches the motor's full load current. This ensures that any overcurrent situation, even a minor one, will promptly trigger the protective device, preventing damage to the motor. In essence, the code aims to prevent scenarios where a low-rated overcurrent device is relied upon to protect a motor when a high-rated device upstream might not respond quickly enough to an overcurrent condition. This is especially crucial in industrial settings where motors are vital components and their failure can lead to significant downtime and financial losses. Therefore, strict adherence to the code regarding motor overcurrent protection and the limitations on series ratings is essential for ensuring both equipment safety and operational reliability. To elaborate further on the concept of interrupting ratings, it's important to understand that an overcurrent device's interrupting rating signifies the maximum fault current that the device can safely interrupt without failing catastrophically. When overcurrent devices are used in series, the overall interrupting rating of the combination may be higher than the interrupting rating of the individual devices, under specific conditions. However, the code restricts the use of series ratings in the motor circuit configuration previously described because the lower rated device might not be able to handle the full available fault current, even if the series combination has a higher overall rating. This can lead to the failure of the lower-rated device, potentially causing an arc flash or other hazardous conditions. Furthermore, the selection of overcurrent devices for motor protection must take into account the motor's starting current, which can be significantly higher than its full load current. Motors typically draw a large inrush of current when they are initially started, and this current can be several times the motor's full load amps. The overcurrent device must be able to withstand this inrush current without tripping, while still providing adequate protection against sustained overcurrent conditions. Time delay fuses or inverse time circuit breakers are often used for motor protection because they allow for short duration overloads, such as those caused by motor starting without tripping. These devices have a time current characteristic that allows them to tolerate high currents for a short period, but trip quickly when the current exceeds a certain threshold for a longer duration. In addition to the interrupting rating and time current characteristic, the voltage rating of the overcurrent device must also be considered. The voltage rating of the device must be equal to or greater than the voltage of the circuit in which it is installed. Using an overcurrent device with an inadequate voltage rating can lead to device failure and create a safety hazard. When selecting overcurrent devices for motor protection, it is important to consult the manufacturer's specifications and the applicable electrical codes to ensure that the devices are properly rated for the application. It is also important to consider the coordination of overcurrent devices in a circuit to ensure that the device closest to the fault will trip first, minimizing the impact of the fault on the rest of the system. Proper coordination of overcurrent devices can improve system reliability and reduce downtime. In summary, the code's restriction on the use of series ratings for motor protection is intended to prevent situations where a lower-rated overcurrent device is inadequately protected by a higher-rated device upstream. Proper motor protection requires the selection of overcurrent devices with appropriate interrupting ratings, time current characteristics, and voltage ratings, as well as careful coordination of overcurrent devices throughout the electrical system. Now let's delve deeper into the practical implications of this code requirement and explore how it affects the design and installation of motor control circuits. When designing a motor control circuit, engineers and electricians must carefully consider the potential fault currents that could occur and select overcurrent devices that are capable of safely interrupting those currents. This involves performing a fault current study to determine the maximum available fault current at various points in the electrical system. The fault current study takes into account the impedance of the power source, transformers, conductors, and other components in the circuit. Once the fault current study is complete, the appropriate interrupting ratings for the overcurrent devices can be determined. In addition to the interrupting rating, the engineer or electrician must also select overcurrent devices with appropriate time current characteristics to protect the motor from overloads and short circuits. This involves considering the motor's full load current, starting current, and thermal overload capacity. The overcurrent device must be able to withstand the motor's starting current without tripping, while still providing adequate protection against sustained overloads or short circuits. As mentioned earlier, time delay fuses or inverse time circuit breakers are often used for motor protection because they allow for short duration overloads without tripping. However, it is important to select the correct size and type of overcurrent device to ensure that it provides adequate protection without causing nuisance tripping. Nuisance tripping can occur when the overcurrent device trips unnecessarily due to normal motor starting currents or other transient conditions. To avoid nuisance tripping, it is important to select an overcurrent device with a time current characteristic that is appropriate for the motor's application. It is also important to ensure that the overcurrent device is properly coordinated with other overcurrent devices in the circuit. Coordination of overcurrent devices ensures that the device closest to the fault will trip first, minimizing the impact of the fault on the rest of the system. This can be achieved by selecting overcurrent devices with different time current characteristics or by using zone-selective interlocking. Zone-selective interlocking is a technique that allows overcurrent devices to communicate with each other and coordinate their tripping actions. This can improve system reliability and reduce downtime in the event of a fault. Furthermore, it is essential to consider the environmental conditions in which the motor and overcurrent devices will be operating. Motors that are installed in harsh environments, such as those with high temperatures, humidity, or corrosive atmospheres, may require special overcurrent protection. In these cases, it may be necessary to use overcurrent devices that are specifically designed for use in harsh environments. These devices typically have enhanced corrosion resistance and temperature stability. In addition to selecting the appropriate overcurrent devices, it is also important to install them properly. Overcurrent devices must be installed in accordance with the manufacturer's instructions and the applicable electrical codes. This includes ensuring that the devices are properly grounded and that all connections are tight and secure. Loose connections can cause overheating and potentially lead to a fire. Regular inspection and testing of motor overcurrent protection systems are also essential. Overcurrent devices should be inspected periodically to ensure that they are in good working condition and that the settings are correct. Testing of overcurrent devices can be performed using specialized test equipment that simulates fault conditions. This testing can verify that the devices are tripping correctly and that they are providing adequate protection. In summary, proper motor overcurrent protection requires careful consideration of various factors, including fault current studies, overcurrent device selection, coordination, environmental conditions, installation practices, and regular inspection and testing. By following these guidelines, engineers and electricians can ensure that motors are adequately protected from overloads and short circuits, minimizing the risk of equipment damage, downtime, and safety hazards. Now, let's explore some common scenarios where the improper application of series ratings can lead to problems with motor protection. One common scenario occurs when a motor is fed from a distribution panel that has a higher rated main circuit breaker. In this case, the branch circuit breaker protecting the motor must be sized appropriately for the motor's full load current and starting current. If the branch circuit breaker is too small, it may trip unnecessarily due to the motor's starting current. If the branch circuit breaker is too large, it may not provide adequate protection against overloads or short circuits. Another scenario occurs when a motor is fed from a variable frequency drive, often abbreviated as volts per hertz. Variable frequency drives are electronic devices that control the speed of a motor by varying the frequency and voltage of the power supplied to the motor. Variable frequency drives can introduce harmonic currents into the electrical system, which can affect the performance of overcurrent devices. In these cases, it may be necessary to use overcurrent devices that are specifically designed for use with variable frequency drives. These devices typically have enhanced harmonic filtering capabilities. In addition to these scenarios, it is also important to consider the impact of voltage sags and swells on motor overcurrent protection. Voltage sags and swells are temporary variations in the voltage of the electrical system. Voltage sags can cause motors to draw more current, which can potentially trip overcurrent devices. Voltage swells can cause overcurrent devices to fail prematurely. To mitigate the impact of voltage sags and swells, it may be necessary to use surge protective devices or uninterruptible power supplies. Surge protective devices protect against voltage surges, while uninterruptible power supplies provide backup power during voltage sags. Finally, it is important to stay up to date on the latest electrical codes and standards related to motor overcurrent protection. The electrical codes are constantly evolving to reflect new technologies and best practices. By staying informed, engineers and electricians can ensure that they are providing the best possible protection for motors and electrical systems. In conclusion, the code's requirements regarding motor overcurrent protection and the limitations on series ratings are essential for ensuring the safety and reliability of electrical systems. By understanding these requirements and following the guidelines outlined in this discussion, engineers and electricians can protect motors from overloads and short circuits, minimize the risk of equipment damage, downtime, and safety hazards. To further solidify your understanding of motor overcurrent protection, let's consider a step-by-step example of how to select the appropriate overcurrent device for a specific motor application. Assume you have a three-phase induction motor with the following characteristics. The motor's horsepower is 10 horsepower. The voltage rating of the motor is 460 volts. The motor's full load amps rating is 14 amps. The service factor of the motor is 1.15. The motor's code letter is G. Step 1 is to determine the motor's full load current. The motor's full load current is given as 14 amps. Step 2 is to determine the motor's service factor amps. The service factor amps is calculated by multiplying the full load amps by the service factor. In this case, the service factor amps is 14 amps multiplied by 1.15, which equals 16.1 amps. Step 3 is to determine the maximum allowable overcurrent device rating. The maximum allowable overcurrent device rating is determined by multiplying the full load amps by a percentage based on the motor's code letter and type of overcurrent device. For a motor with a code letter of G and using an inverse time circuit breaker, the maximum allowable overcurrent device rating is 250% of the full load amps. In this case, the maximum allowable overcurrent device rating is 14 amps multiplied by 2.5, which equals 35 amps. Step 4 is to select the appropriate overcurrent device. Based on the calculations above, the appropriate overcurrent device for this motor is a 35 amp inverse time circuit breaker. It is important to note that this is just an example, and the actual overcurrent device rating may need to be adjusted based on the specific application and the recommendations of the motor manufacturer and the applicable electrical codes. In addition to the calculations outlined above, it is also important to consider the motor's starting current when selecting the overcurrent device. The motor's starting current can be several times its full load current, and the overcurrent device must be able to withstand the starting current without tripping. The motor's code letter provides information about its starting current characteristics. Motors with higher code letters have higher starting currents. For motors with high starting currents, it may be necessary to use a time delay fuse or an inverse time circuit breaker with a higher instantaneous trip setting. This will allow the motor to start without tripping the overcurrent device. It is also important to consider the coordination of overcurrent devices in the motor circuit. The overcurrent device protecting the motor should be coordinated with the upstream overcurrent devices to ensure that the device closest to the fault will trip first. This will minimize the impact of the fault on the rest of the electrical system. Coordination of overcurrent devices can be achieved by selecting devices with different time current characteristics or by using zone selective interlocking. Zone selective interlocking allows overcurrent devices to communicate with each other and coordinate their tripping actions. Furthermore, it is important to ensure that the overcurrent device is properly installed and maintained. The overcurrent device should be installed in a location that is accessible for inspection and maintenance. The device should also be protected from environmental factors such as moisture and dust. Regular inspection and testing of the overcurrent device are essential to ensure that it is functioning properly. The overcurrent device should be tested periodically to verify that it is tripping at the correct current level. In conclusion, selecting the appropriate overcurrent device for a motor application requires careful consideration of various factors, including the motor's full load current, service factor, code letter, starting current, and the coordination of overcurrent devices. By following the steps outlined in this example and consulting the applicable electrical codes and standards, engineers and electricians can ensure that motors are adequately protected from overloads and short circuits.